thanks again for the invite. I really appreciated the broad remit, and I kind of took the opportunity to basically come up with a brand new talk. It's not going to be a typical kind of data theory talk. I'm instead going to talk a bit about practice, I guess. So what I've done is actually to prepare a GitHub repository with some code in it. And later on, we're going to take a quick look at that. So it's kind of following along the theme of these accessible tutorials that I wrote some time ago. But I think that with what I've learnt and with the kind of development of the software, I think that these things are even more approachable. So that is, in fact, if there is any kind of coherent idea behind this talk, it's that Bayesian methods are more accessible and approachable than ever before. And this is my kind of brief, very schematic timeline. In the past, if you wanted to engage in any kind of Bayesian inference for whatever purpose, whether that's data analysis or for modeling, you really needed quite a lot of expertise in programming. To a certain extent, that's still true, but that has changed a lot recently because of packages, programs like JASP has appeared. So hopefully everybody is aware of JASP, but if not, it's a really nice kind of point and click graphical interface. It's a bit like SPSS in that respect, but it's actually usable in my opinion. And one of the really interesting things about this is that as well as having a full range of frequentist statistics, it also has Bayesian equivalents. So that's probably the easiest way that someone could get into doing Bayesian data analysis at this point. I'll talk a bit more about the distinction between data analysis and modeling in a moment. But on the modeling side, the idea is that in the past, you really did have to have quite a lot of domain expertise. So you've got to be able to think of kind of interesting scientific and research questions, but then you also need quite a lot of programming skills and quite a lot of knowledge in these packages such as Winbogs and JAGs. Now, those were great advances and in fact opened the door to many more people, including myself. I got started doing Bayesian things, or actually maybe before JAGs, but yeah, that was a really great advance. And then along came STAN. So this is kind of a Bayesian inference piece of software that's led by Andrew Gelman and co. And lots of people are now aware of this. You can write your models in such a way to do kind of more efficient Bayesian inference. On the kind of Python side of things, there's a similar package, does a very similar job called PyMC3. And I've been using that one quite a bit recently. But then even more recently, you start getting what could be called meta packages almost. So one in particular, so BRMS, is a really good one. So this kind of sits on top of STAN, and so it can do more than this. But if you're interested in doing some linear modeling of your data in a Bayesian fashion, you can very quickly get up to speed and start kind of running these things. Now, I think that this is absolutely wonderful. I'm not going to talk much about it in the talk today because I'm a bit of a tinkerer and I kind of like to know how things work. So some of these packages, whilst they broaden up the kind of opportunities for a wider range of people, they kind of do that by hiding some of the details. So there's this inevitable trade-off. So some of what I'm going to be trying to do today is to engage with those details and show you that they're not actually that bad. And more specifically, what I might show you in a moment is another kind of Bayesian package called Turing. And I've been really very kind of, well, I don't know if excited is the right word, but this has been a really kind of interesting Bayesian package to get to play with. So you can basically specify your Bayesian models in a really concise manner. So yeah, a lot of the popularity and the buzz in recent times in terms of Bayesian approaches has been very much focused on data analysis, and this is great. The way how I would characterize that is that you have some kind of model. Typically, it's some kind of linear model, like a generalized linear model, and you've got some behavioral data, and you want to use Bayesian inference in order to estimate all the various kind of intercepts and slopes and all of that kind of thing. And we're going to have a brief look at Bayesian linear regression to introduce some of these concepts. Now, if you want to go a little bit further than describing your data, I guess, you can use modeling approaches in an effort to potentially explain the processes that gave rise to your data. And so cognitive modeling is practically very similar, but conceptually you're proposing a specific kind of mechanism, for example, maybe a cognitive mechanism which your participants are employing in a particular experiment, for example. And so now the key difference is that your model describes processes that are potentially happening in the brain. And so they're potentially explanatory in nature. To explore that, we're going to have a look at what I'm interested in right now, which is temporal discounting. So very much like the marshmallow experiment. But we're going to move on and look at a third class of model, which becomes a bit meta, because now, rather than you as an experimenter being a Bayesian, you might actually propose that the participants that you're observing are actually Bayesians themselves. And so if you put someone in a task, we're going to talk about acute localization attention experiments. The proposal would be that the participants are using Bayesian inference, combining their sensory data with their prior beliefs and basing their decisions on that. So those are the things we're going to look at, and hopefully it will be a fun whirlwind tour. I'm going to focus somewhat on the how rather than the what. So I'm not going to try to convince you that Bayesian approaches are kind of better than anything else. I'm just going to focus on how do you practically do that. And I'm going to show you kind of select highlights of some code in order to do that. The key thing will be the simplicity of it. You're not going to become a Bayesian kind of expert in modeling after this talk, but hopefully if you're interested in it, it may provide kind of motivation and it can maybe inform you somewhat. If you are already doing modeling, I think that there might be some gems in here, because we're going to be looking at the new programming language Julia and the really cool kind of Bayesian inference package called Turing. So I've been really impressed with these things recently. So hopefully all of this will be accessible. So I'm going to switch over now to a web page, and I'm hoping that everybody can see this okay. I did a test earlier. What I've done is to put together some code in a GitHub repository. So for the few of you who will be really interested in following this up, you can go and have a look later and look at some of these notebooks that I've created. But what I'll do at the moment is give a whirlwind tour of some of these ideas. First up, we're going to look at Bayesian linear regression. How do you do this? So first of all, what you would do is you would have run an experiment, you would have collected some data and so on. And we're looking at an extremely simple example where you have one predictor variable, which we're going to call X, and one outcome variable, which we're going to call Y. Now, for this particular example, I'm actually going to generate simulated data. And the reason for that is because I want to kind of know what the true regression coefficients are. And so we can compare our inferences with ground truth. So we're going to start off with defining this linear regression equation, which is incredibly simple. You just have an intercept, so beta naught, and a slope, beta 1, which is multiplied by your predictor. So that's the equation of a straight line. We're going to use that in order to generate this data, and that's what we're going to work with. Our first step is to basically create what we would call a generative model or forward model. And this is the entire code that you would need in order to do that using Turing. So we're going to say for our data, X and Y, we're going to define some priors. So we're going to have a prior on the intercept and a prior on the slope, and also a prior on our observation noise. And then finally, we're going to define our likelihood. So we're going to say that Y is normally distributed around our equation of a straight line with some standard deviation that we don't necessarily know. And that's all there is to it for a Bayesian linear regression model. What you might do in a Bayesian approach, first of all, is to basically examine what prior beliefs you have specified. And so these distributions basically encapsulate the prior beliefs that you have specified. So we're saying that the slope and the intercept are centered on 0. These are the most likely values that we expect. And as those values get larger, this becomes progressively less plausible. Now, you always get questions from reviewers and so on about, where do the priors come from? How do you justify these? And so a very interesting and important step is to not just think about your priors, but to think about how do the priors actually affect my predictions about the data. And so what we can do is all of this code just does some plotting, basically. So we're plotting a whole bunch of linear regression equations that are consistent with our prior beliefs. And in this example, I've specifically chosen some kind of data that doesn't quite fit with those priors. And so this would be a very useful step to tell us that our priors potentially don't quite match up with the data. And so you could go back and examine what that is about. So there's some delivery person knocking on my door, which I'm going to ignore. Right. So in this particular example, I'm not going to do anything about this, but in a real world example, you might want to update what your prior beliefs are. And then you essentially want to do the Bayesian inference. And so with this single line of code, we're basically saying, I would like Turing, the Bayesian kind of black box bit of code here, to work out what we should believe about our slopes and our intercepts based upon the data that we're providing it with. Now, this is the outcome. So what we're seeing is that after having seen the data, we have these kind of narrower distributions of belief over what our parameter values actually are. And there are kind of multiple lines here shown by multiple colors. And this is a very important kind of sanity check to ensure that the actual calculations have worked correctly. So what it's actually done is we've asked the computer to solve the problem 8 different times simultaneously on the cores of my computer. And the question is, do these 8 separate solutions kind of agree with each other or not? In this case, they do agree with each other, and so we can kind of be confident in the solution that we've come up with. We can also kind of plot the distributions of the priors. So what did we believe about the intercept term before we saw the data? And this kind of orange region, I guess, is what do we believe about the parameters after we've seen the data? And what I've done, because we used simulated data, I know exactly what the true parameter values are, and that's shown by the vertical lines. And so we can see that the Bayesian inference has essentially worked in that we now have, we now believe that the slopes and intercepts are actually much closer to their true values. So this is all good, and we can move forward more confidently in a real situation where we don't necessarily know the ground truth. We're trying to estimate that. A final kind of sanity check, if you like, would be to repeat the procedure we did before and to say, show me some example linear regressions that are now consistent with my final beliefs after having seen the data. And so we can see that these light grey lines here are now much more clustered around the data, and it can obviously give us an idea about how confident we are about each of the parameters. We can also see that our kind of best guess estimate shown by the blue line is actually very close to the true line. And so we know, we have faith that the inference processes that we've done are kind of working okay, and that we've got a good model of the data. So briefly to wrap up this example, there was a bit of code that flew by, and a lot of this was basically for plotting. But the real code that does the work here is basically formulating the generative model. And this is going to be the theme across the 3 examples. So I won't go into this again, but I just want you to observe the conciseness and the compactness. I think it's rather pleasant. So what we're going to do now is to move on to a second example. And this example is going to look at temporal discounting. So this is what I'm particularly interested in at the moment. And the best way to demonstrate that, I think, is to show you this interactive web app that I made a number of years ago now. So conceptually, what we're doing now is we're moving from a description of data based upon linear models to proposing a specific mechanism that gives rise to behavior. And the specific task that we're going to look at is hyperbolic discounting. And so in these experiments, people are often given questions where they have to decide, would they like, let's say, £10 now, or would you like £50 in 1 week time? And they would have many of those questions. And the idea is to kind of work out how kind of present or future focused is this particular individual. And we are going to look at a model called hyperbolic discounting. And our cognitive model can be captured basically by this plot on the left-hand side, which says that let's go with the example of coffee. If someone gives me coffee now, then it will have its full value to me. If someone promises me coffee tomorrow, then that will actually be worth slightly less. And so if I'm making decisions between immediate coffee and delayed coffee, I might want to downweight or discount the value of future coffee. So the question is, how do I do that? If you were a coffee addict, the proposal is that the value of future coffee would rapidly plummet as the coffee goes further into the future. If you are more ambivalent about coffee, then perhaps the value of future coffee declines at a slower rate. And so the way in which we work out where people are on this spectrum of high to low discounting is to ask them a bunch of questions. And we can visualize that on the right-hand side of the plot. And so what we can do is we can ask people a load of questions like, would you like £50 now or £100 in the future? And according to this model, the proposal is you work out, well, the present value of £50 to me now is worth 50, but the present value of £100 a year from now is worth much less. And so in this situation, I would choose the immediate money. But that wouldn't be the case if I discounted in a different fashion. If I was more future oriented, for example, then I might actually pick the long-term reward. And the explanation for that is because I've discounted the longer term reward to a lower degree. So that's the basic idea. We're going to be looking at a real data set just from one participant to keep things simple. And they were asked a whole series of questions like, would you like £80 now or would you like £85 in 157 days? And they had a series of questions like this. And the outcome that we're recording is what their response is. Would they like the immediate or would they like the delayed? And so the first thing we're going to do, just like in the previous example, is load in our data. And very briefly, we have the immediate reward amount. So the first question is £80, and that would be delivered immediately, or £85 in 157 days. And in this example, the participant chose 0, which means they chose the £80 now. And so this just shows the rest of the data from a number of trials. And we can visualize that data on a graph similar to the one that I showed you before. And so on the x-axis, we have the time until the delayed reward appears. And on the y-axis, we basically have the ratio between the two rewards. This is just a useful way how to plot this type of data. What we can see is that there are a cluster of responses where the participant chose the immediate rewards, and there's another cluster of responses where the participant chose the delayed reward. And so our task will be to work out what is the discount rate of the hyperbolic model which explains this data. So the first task, very much like with our linear modeling, we're defining what's known as a generative model. So what is the process that we believe generated our data? So first we define our priors, the most important one being our prior over the discount rate. So this is whether your discount curve is steep or shallow. Then what we have is 2 lines proposing that what we're going to do is we're going to compare the present subjective value of each of these rewards. And so what we're doing is we're taking our reward, we're multiplying it by our discount rate. So the hyperbolic function, we're going to come to that in a moment. The idea then is, well, how do you make a choice? Well, we're going to compare the subjective value, the present subjective value of each of these things. So we're going to just subtract one from the other. And so if this is positive, then one of the choices is better. And if it's negative, one of the other choices is worse. And so you could just say, I'll take the best choice. But anyone who's kind of collected human data knows that the data can be noisy. And we're going to model the fact that your probability of choosing one thing or another thing is noisy by using a psychometric function, which we're going to come to. The final part is our likelihood term. So what we're doing here is modeling our response. Did you choose the immediate or the delayed, as a Bernoulli, which is essentially a biased coin flip. And so we want, part of this model is saying, well, in this particular example, if they have a 70% chance of choosing the delayed reward, then that's reflected in this likelihood. So we're nearly there with this model. All we're doing here is describing our hyperbolic discount function. The details aren't important, but it simply describes how our discount rate decreases as the delay increases, and how that might be changed depending upon our discount parameter. Then finally, we're going to define this psychometric function, and the details aren't really important for those of you who want to look and can look at the code. But all we're doing is we're defining a function. We're defining the probability of choosing the delayed reward based upon how differently valued are these rewards. So if they have very similar values, then we're going to be ambivalent and you might respond 50-50. But if one reward is clearly better than the other, then you have a much higher choice of choosing that one. So we're going to do the same trick of examining our priors so we can make sure we're prepared for reviewers who might question what our prior beliefs are. And we can also do that in a more intuitive way by a thing called sampling from the prior to say, what are our prior beliefs about plausible discount functions? How steep is this curve before we have seen any data? And in this case, we see that our prior beliefs correspond to a very broad range of plausible discount rates. Maybe it should be broader, maybe it should be narrower. It's situation dependent. But hopefully the reviewers are now happy. And so we want to do our Bayesian inference using the same kind of one line of code in order to do the Bayesian inference. As is normal with many of these packages, you get some of these kind of warnings. In this case, these were all benign and we don't have to worry about it. So we can do the same trick. We can say, should we have faith in the inferences that we have made? And so we ask the computer to do this 8 times on each of its cores. And we can see that each of those times it came up with the same basic answer. And so we can have faith that we're calculating something meaningful rather than something spurious. We can again compare our prior beliefs about the parameters to our beliefs after having seen the data, which is quite a useful exercise. But then we can also check to see, as a useful sanity check, we can say, does this model accurately fit the data? Does this make sense? And in this case, we can see that we have a much narrower range of plausible discount rates here. And For those of you who look in the text, there's kind of a reader question, a reader task to think about why this isn't more tightly peaked, for example. So you can think through that in your own time. But that raises an important point, though, about the Bayesian approach, in that you don't necessarily get just one answer. These are the parameters. You get a whole distribution of answers. And in some ways that can make your life a little bit more taxing, but in other ways it can make your life or your research project a little bit richer, because now you know how confident you are in those answers. And so if the data is not very informative, it would be very useful to know that fact before trying to make strong research conclusions that you don't actually really believe in based upon the data, or at least that aren't fully justified by the data. So again, we zoomed past a lot of code, and as is always the case, much of this is to do with plotting. The only real hard work here is to create our generative model. And what I would say is that we've actually done some quite kind of interesting, quite kind of complex modeling, but it's all being done in just a handful of lines of code. We're defining our discount rate. We're defining a response function that says how participants can be noisy about their responses. And then we're basically embodying our modeling ideas about how you discount rewards that appear in the future and how you compare these in order to make a response. So yeah, I think that's great. Compared to previous software packages that I've used, this is much simpler. You can get really complicated things running in a very short space of time. So I'm going to kind of whiz through our final example. And this is essentially a Bayesian brain kind of example. So what we're going to be looking at here is a task called queued localization. And in this task, an experimenter would sit in a dark psychophysical room with their chin on a chin rest for quite a long time, and they would get quite bored. But their task would be to observe the screen, and they might see a cue item. It might be a flashing blob, for example, and this cue could appear in one of a number of places. And we would have told the participant in advance that the cue tells the truth X% of the time about where a target might end up being. And so after a short pause, the participant will see one of a number of things. So if the cue was valid 70% of the time, so let's say the cue tells the truth about where the target might appear 70% of the time, then they might build up expectations about where the target might appear and where distractors might appear. And so their task is to basically respond where they think the target was. So they press one of 4 buttons, and they'll either be right or wrong, and we give them feedback. I think, compelling theoretical research question here about attention is that what is it that is producing people's responses? Is it some notion of attention, whatever that may be, being drawn to one place or another place? Or alternatively, can we actually treat this attentional task as people simply making inferences about the state of the world? And what I'm going to show is what we're going to look at in this notebook is how to calculate this optimal observer prediction, this black curve. And what we're not going to look at the moment is how you fit that to human data. That's a separate task. But we can look at how do you make Bayesian optimal observer predictions. So in keeping with our theme, we're going to describe a generative model. So if we go back up to our task, we are literally just describing what is happening in this task in code form. So briefly, a queue will appear equally likely in one of our locations. This will define a set of prior beliefs. So if we've told someone that the queue is valid a certain percent of the time, then they will believe that the target will appear there with that probability. The target is then kind of randomly drawn according to how often the queue tells the truth or otherwise. And then finally, depending upon where the target is, we're going to generate some noisy sensory information. And all this line does is to say we're going to observe some normally distributed noise at each of the 4 locations, but that observation is going to be centered on 1 where the target is, and it's going to be centered on 0 where the distractors are. And so in just a handful of lines of code, we've essentially just described what are the steps that happen in our experiment. And this wasn't the way how I did this when I published this work, but now you can basically go through this incredibly simple process where you can essentially simulate a trial. We're going to simulate trials, including we're going to generate data that the observer sees. So we're going to tell it what the queue validity is and so on, but we're not going to tell it where the queue was, where the target was, or what the sensory observations were. And so we're essentially just running through our experiment code, generating queue, target, and sensory data. Now we're essentially modeling what's happening inside the observer's head, if you like. And so we're giving it knowledge of the model, of the task, but now we are providing the observer both with the location of the queue. So we assume they saw where the queue was. We provide them with the sensory data that they got, but we don't provide them with the actual target location. And so again, we can do Bayesian inference to say, how would an observer make inferences about where the target was, given the information that they have? Finally, we're going to assume that people respond to the location that they think has the highest probability of containing the target. And we're going to assess whether this is correct or incorrect. Now, that's the core logic. All the rest of this code here is essentially repeating this many times in order to work out how often the participants are correct. So we're going to repeat our trials a number of times, and we're going to repeat this over a number of potential queue validities. And so all of this is just plotting code. And what we're going to end up with is these graphs where this is now Bayesian optimal observer predictions of the performance in this task as a function of queue validity. And so what we can see is that if you have 2 locations, so a bit like kind of Posner queuing, a queue will appear on the left or the right. The target will appear on the left or the right, and then you see the target and the distractor. And what we can see is that no matter what your sensory acuity is, you have the lowest performance when the queue tells the truth half of the time. And so this is where the queue is actually uninformative. And so kind of intuitively, we can say if you've got 2 possibilities and the queue tells the truth half of the time, that hasn't told you any information. So you your prior beliefs are essentially 50-50 left and right. And so the only way how you can do this better than chance is by using your sensory observations. And we can see that the higher your sensory acuity, the higher the performance. But as the cue does become predictive or even anti-predictive of where the target will be, your performance increases. And so this is kind of now quantitative predictions that a Bayesian observer would combine their prior beliefs arrived at from the cue with their sensory observations in order to come up with best guesses about where the targets would be. The same basic thing happens now with 4 locations, but again, it follows our kind of intuitive predictions. So if you have 4 locations, the cue won't tell you anything if it tells the truth 1 out of 4 times, so 25% of the time. And indeed, that's what the quantitative prediction is. Yeah, so I won't go into that in more detail, but yeah, consult the notebooks if you're interested. And what we can see is that in very few lines of code, we've actually replicated this figure from one of the review papers that I wrote in a significantly lower amount of code, I should say. So yeah, let's flip back to my presentation and wrap up. So in a way, this talk may be a bit like this diagram, in that I've kind of shown you the beginning parts, and just because of time, I couldn't necessarily go into all the details. But what I hopefully have conveyed is that the amount of code and the kind of code that you're writing in order to do this Bayesian modeling is actually very minimal and very approachable. And part of that is because of the niceness of Julia as a programming language, which has then enabled Turing, which does the Bayesian inference, to do so with very minimal code. If you are particularly interested in this topic and want to learn more, I would probably recommend, well, I do recommend Bayesian Cognitive Modelling, a practical course. This is a really great book. So wrapping up, hopefully, for those of you who aren't modelers, hopefully you enjoyed seeing a little bit about what goes into the ingredients, the peek behind the curtain. I think if you are kind of like a beginner modeler or an inspiring modeler, hopefully this may convince you that it's very doable and very achievable, hopefully. And if you're already an active cognitive modeler, hopefully you will kind of get something from my excitement about Julia as a programming language and Turing in order to do Bayesian inference. I'm not going to bash MATLAB, Python, or R, but my plan going forward is to do as much work as possible using Julia. I think it's a great programming language. So on that, I'd like to wrap up and say thank you again for the invite. If any of you are really interested, you can go and look up the code on my GitHub thing. And also very cheekily, I'll say that I like working on a couple of different things at a time. And so I'm very open to ideas for collaborations and things. So thank you very much.